So we have refrigerant 134a flowing at steady state through a horizontal tube having an inside diameter of the tube of 0.025 meters. The refrigerant enters the tube with a quality of 90% and a temperature of 36 degrees C and a velocity 15 meters per second. That's how it enters. It exits the tube at a pressure of 9 bar as saturated liquid. And then the problem asks for a number of things. What's the mass flow rate of the refrigerant, the velocity of the refrigerant at the exit, the temperature of the refrigerant at the exit, and the rate of heat transfer to the refrigerant in units of kilowatt. Okay, so we make a sketch. Here is our tube. And we have inlet on one side. We'll call it state 1 flowing in, exit state 2. And they give us some information about the conditions. So at state 1, it has a temperature of 36 degrees C, and I'm going to put pressure as a placeholder because over here pressure at 2 is given to be 9 bar. Okay, so pressure at 1 unknown yet, temperature at 1 36 degrees C, quality at 1 is 90%, and the velocity at 1 is 15 meters per second. And over here at 2, they say that it's saturated liquid. If you wanted to, you could say, oh, we have the quality at 2 known. That's 0, saturated liquid. Okay. The diameter of the tube is given. Diameter of 0.025 meters. And we know that this is all refrigerant 134a. So to get the mass flow rate of the refrigerant flowing, typically we determine it either at state 1 or state 2, but if you do a control volume analysis, so this would be where I'm showing a control volume, it's cutting just on the inside of the wall of the pipe, and then it cuts at the ends where the flow goes perpendicular 90 degrees across the end into the tube and then out of the tube at state 2. There is the possibility of a heat transfer, and I'm going to show it like this. A Q dot coming into that control volume. What I showed with the dashed line is a control volume. And even though there's not the possibility of a shaft power going out, I'm going to show it as W dot, but then it's equal to 0 because there is no shaft power in or out. It's just a tube and flow through the tube. Okay. But the Q dot and the W dot are for our energy balance. Okay. So let's just focus on part A. What is the mass flow rate of the refrigerant? Well, from a mass balance, we know that the mass flow rate coming in at state 1 is the same as the mass flow rate out at state 2, and so we just drop the subscripts and we're just looking for the mass flow rate. We can calculate it either at state 1 or at state 2. Often we calculate the mass flow rate if we're given information to allow us to get the cross-sectional area, some velocity, maybe the area at 1, the velocity at 1, and then we divide by the specific volume at 1. And that'll be our strategy here. So our area at 1 is pi, diameter at 1, which is the same as the diameter everywhere, squared divided by 4. So we can calculate that area. That area comes in 0.0004987 meters squared. Okay. Then what we need is we need the specific volume, V sub 1. Well, that's a property. We know the temperature and the quality at state 1. That allows us to calculate V sub 1. We've done that a few times. The equation is V sub G, not V sub G, V sub F, the saturated liquid specific volume, plus the quality at 1, times V sub G, saturated vapor, minus V sub F, the saturated liquid's value. When you make this computation, going to, what table would we go to? Well, it's 36 degrees C, so we go to our saturation table. So it's saturated refrigerant 134a. That would be table A10 in our textbook. And we look down for a line of temperature of 36 degrees C, and we read off our V sub F and our V sub G. Remember, there's this 10 to the 3 up here, so the value for V sub F is 0.000859, not just that numeric value right there. And that's units of meter cubed per kilogram. That's V sub F. And then V sub G, much larger, it's 0.0223 meter cubed per kilogram. So when we make this computation, V sub 1, the specific volume of the fluid coming in, 0.02016 meter cubed per kilogram. So then we can come over here, we can calculate the mass flow rate. Is that area 0.0049087. That's sloppy. Let me rewrite that. 0.087. That's meters squared. Our velocity at 1 is 15 meters per second. That gives us in the numerator meter cubed per second. And we divide by 0.02016 meter cubed per kilogram. And so our mass flow rate of the refrigerant is 0.365, I'm going to say kilograms per second. Box it, call that the answer to part A. Okay. Part B, what's the velocity of the refrigerant at the exit? Well, it's the same type of equation. We just write like this one. M dot's equal to A V over specific volume. What we want is, if you want the exit speed V2, that's equal to the mass flow rate, specific volume at 2, divided by that area. Now the area 1 is equal to area 2, same area. So the mass flow rate has not changed. You can put that in 0.3653. You would carry more digits in your calculator. The specific volume at state 2 we need to calculate. I'll just fill in, put that area right here, 0.0004987. Okay, how do I get that specific volume, V sub 2? Well, it's V sub F, the saturated liquid's value, at our 9 bar. So we could go to table A11. So we have saturated refrigerant 134a properties. But this time, the primary index on the first column is pressure. So we come down to a pressure of 9 bar. And we read across to get our saturated liquid specific volume. And it's right there. And so it's 0.0008576. And if you look, that was very close to the saturated liquid value at 36 degrees C. Well, the pressure, if it's coming in at 36 degrees C, this is the inlet pressure, 9.117 bar. So you could have filled that in right here, 9.117 bar. It really didn't drop much. There's a little pressure drop as it goes through this tube, goes from 9.117 bar down to 9 bar. Okay, but we get our V sub 2. We just had that. What is it again? Let me look. Specific volume at state 2. Yeah, that 0.0008. Oh, I forgot the number. 576. 576. So we'd put it right in here. 0.0008576. And our units would cancel, and we'd get the exit velocity to be 0.638 meters per second. And we box it, and that's the answer for part B. Okay. Well, what about the answer for part C, what is the temperature of the refrigerant at the exit? So I'm kind of leaving a space right here. What is T2 equal to? Okay, well, just like we deduced P1, because it's the saturation pressure at 36 degrees C, you do the same thing and you say T2 is the saturation temperature at 9 bar. Okay, so let's take a look at our table. We're back to table A11 and we're at 9 bar and our saturation temperature is 35.5 degrees C. So you would make a note on your exam, like go to table and T2 is equal to Tsat at 9 bar, and then just write down the value 35.5 degrees C from the table. Maybe make a little notation. What is that, table A11? Okay, and that's the answer for part C. So the temperature, if I just make the quick comparison here, didn't go down much, did it? 35.5 degrees C, just like the pressure didn't go down much. It came in at 36 temperature and went down to 35.5 degrees C temperature. Okay, so at this point, let's go for part D. What is the rate of heat transfer to the refrigerant in units of kilowatts? So they're asked for this large Q dot right here. That's our symbol in our textbook, Q dot, for a rate of heat transfer. So we have this control volume and we do a first law analysis, or we do a EB, my notation for an energy balance. Okay, it's steady state. So if you write the general equation down, you have the rate of change of energy in the control volume with respect to time, which when it's steady state, which almost always it is, that side's equal to 0, is equal to the rate at which it's coming in with heat transfer minus the rate at which it's going out by some shaft power, W dot. For this problem, there's no shaft power. And then we continue. We have the mass flow rate coming in, bringing with it not only its internal energy, but its flow work. We combine those two into a new property called enthalpy. So that's H1. And then we think about it. Is there any potential energy I need to consider? Any kinetic energy I need to consider? Well, it's a horizontal tube. And so right away, the potential energy effects are negligible because it doesn't change elevation from inlet to outlet. Okay. But what about the kinetic energy? Well, let's include the kinetic energy coming in. So it's both the enthalpy plus the kinetic energy coming in. And because there's only one mass flow rate, we just subtract off the exit enthalpy and subtract off the exit kinetic energy. So if we're looking to calculate Q dot, it's the mass flow rate times the exit enthalpy minus the inlet enthalpy plus the exit kinetic energy minus the inlet kinetic energy. This is a 1, not an I. That's a 1. All right, this is a 2. So you go to the tables and you say, how do I get the enthalpy coming in? Well, it's the same equation like the specific volume. You get H saturated liquid plus that quality of 90% times Hg minus Hf. Saturated vapors enthalpy minus saturated liquids enthalpy. So let's go to the table A10 at the 36 degrees C, and we come over here and we have the saturated liquid enthalpy 100.25 and the saturated vapor enthalpy. And because the difference Hg minus Hf is often used, they include this additional column, which is HFG. That's exactly what it is. HFG is what it takes to evaporate, to go from saturated liquid to saturated vapor, that change in enthalpy. So for this problem, we could say that H1 is equal to 100.25 plus, it was a quality of 90%, 0.90, times HFG. 166.15. All those have units of kilojoules per kilogram. So H1 comes in at a 249.785 kilojoules per kilogram. So we can put that over here. I'll rewrite it. 249.785 kilojoules per kilogram is H1. What about H2? Well, H2, just like V2 was V sub F, this is H of F at the 9 bar. So we go to our table A11 at 9 bar, and we look across and we pick out the saturated liquid enthalpy of 99.56. So this is 99.56 kilojoules per kilogram. Okay, so it's like we did a little work and we got it, did a little work and we got it. What about these kinetic energies? Well, let's go ahead and get the specific kinetic energy at the inlet, KEI. There's a lowercase, the way I write them, not I, at state 1, and that's the 1/2 V squared. Now, that will naturally have the units of meters squared per second squared, so you want to convert it so it has the same units as the enthalpies, because you're going to combine them in this equation. So we would convert that to kilojoules per kilogram by using a unit conversion factor. That 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. It's like you divide it by 1,000. Okay, so when you do that, the kinetic energy, whoops, I'm running out of room here, kinetic energy at 1, because they gave us the velocity, is not very large, 0.1125 kilojoules per kilogram. Now it's a little bit of work, but you can get the velocity at 2. I didn't leave enough room. Let me try and move this a little bit, move it up. And the velocity at 2, how are we going to calculate that? Oh no, we already did. It was 0.638 meters per second. So now in the same calculation, kinetic energy at state 2 leaving is not very large. It's 0.0002. It's negligible kilojoules per kilogram. Okay, so when I stick in the value here, really we could neglect KE2 for sure. We have the KE1, we put that in, multiplied by the mass flow rate, we calculated that in part A, and you get what is the rate of heat transfer from somewhere, from the surroundings, from the hot wall or of the pipe into the refrigerant. The direction is dictated by the sign convention in Thermo 1 for the first law of thermo. And we calculate that this is a negative 54.9 kilowatts. So that's our answer for part D. Now, what does it mean that it's negative? Well, a negative means it's not heating the refrigerant, it's cooling the refrigerant. And so the direction of the heat transfer is opposite of what we've shown in our control volume illustration. Okay, that's what it means to have a negative Q dot. Now, some students will look at this and say, well, that's a large amount of heat transfer out of that fluid. How come you didn't cool it down more? What do you mean cool it down more? And they say, well, it came in at 36 and it left at about 36, a half a degree C. That doesn't seem right. Well, that's, if you just look at temperature, they would talk about the sensible cooling. But here the refrigerant, a lot of that energy is being removed from the refrigerant because it's changing phase. It's condensing. It's going from 90% by mass, which is in the vapor state, to 0% by mass that's in the vapor state. It's all liquid. And that's what they call latent load, or a latent heat transfer, because it's quote unquote hidden, and it's like no temperature change, but a whole lot of heat transfer associated with condensing it in this case. but you could also have it as evaporating or boiling it in another problem. But for here, it's negative and it's being cooled and it's condensing the liquid, the refrigerant. And so it all comes out saturated liquid. Well, with that, we're done with this problem.